Okay, it's time to start. Welcome everyone at our weekly colloquium. Our speaker today is Professor Paweł Kurzyński from Adam Mickiewicz University in Poznań, and he will tell us about photons, and the title of his talk is From Quantumness of a Photon to a Classicality of a Light Wave. Yeah, please.
Thank you very much. So, good afternoon, everybody. First of all, thank you very much for inviting me here. It's a great pleasure and an honor for me to be here. So I would like to tell you about some research that I did together with my friends. This research was published in two papers, one quite recent and one from 2017. So what's this research about? So I'm quite sure that you heard about many papers in which people were showing that it's possible to simulate some aspects of quantum systems with classical waves. And of course there is nothing so surprising about it, simply because in quantum theory we have wave-particle duality, so of course wave properties of quantum particles should be in some way simulated by waves, by classical waves. However, I would like to focus on these papers here. I would like to focus on these three papers that started some issue, and right now there are many papers following up. Namely, these people show that actually you can use classical waves to violate Bell inequalities. And this is a problem, namely because on one hand Bell inequalities are used and are considered as some test of non-classicality. Non-classicality in the sense that such a system cannot, if the system violates Bell inequalities, the system does not admit so-called hidden variable description. So, I mean, it's a hidden variable description. But, I mean, this is the only time when the notion of hidden variables appears here, because later, just in a moment, I will explain what I mean by it. But anyway, in simple words, the idea is that when some system violates Bell inequality, it's considered to be non-classical. But on the other hand, we know that classical light, as described by Maxwell equations, is actually quite a classical system. It should admit some kind of classical it admits classical description, so it should also admit this hidden variable description. So there is a problem, because either this result implicate that Bell inequalities can no longer be used as some test of quantumness, or, I mean, of course, or there is other possibility that maybe there is something quantum in classical light. Or there is another possibility, and this is what I'm going to show, that actually the authors overlooked something. And what they overlooked is the fact, and this is going to be crucial here, that a light beam is made of many photons, and you need to take into account indistinguishability between these photons. And this have extreme implication on how you derive Bell inequalities. But let me start with the following general scenario.
Inequalities is not only inequality itself, but it's also the fact that these are spatially separated regions.
Okay, so what I'm going to I would like to.
And at least in this paper, this is not satisfying.
Yes, so I'm going to go there. But actually, Bell inequalities is a very special case of a broader thing, namely quantum contextuality. And in quantum contextuality, you can have local systems. So, and for quantum contextuality, you can also have Bell inequalities. So originally, Bell inequalities were.
There is no problem with interpretation of such things classically if this is in one place. The problem is that it's actually at a distance when you have separate detectors.
Well, I believe that there are.
One beam with polarization, as in Everly's papers, then nothing strange is happening. It's like the relation between at least Everly's paper and true Bell inequalities is similar as relation between known properties of light pulses, which are purely classical, and they seem to obey the uncertainty principle, and quantum mechanical uncertainty principle.
Right, so
it's just the same mathematics, but physical content is absolutely different.
Yes, I mean, so I believe that there is something more to it, and my whole seminar is devoted basically to show how I see this problem and what's the explanation. So I believe that in the end we will agree. Okay. Yes. Basically, what I wanted to tell you is that Bell inequalities or all the discussion about contextuality are often considered within quantum theory, but in fact they have nothing to do with quantum theory. So there is also a lot of philosophical discussions about Bell inequalities, but what I want to do is I always try to demystify them in the following way. I would like to show you that this is actually a very simple mathematical problem. Namely, what we have is we have some set of data, and then we make some assumptions about this data, and then under these assumptions, we try to explain whether the set of data is describable within Kolmogorovian probability theory or not. And basically, Bell inequalities are tools to make a decision whether such a system under this assumption, whether such a set of data under given assumptions is describable by Kolmogorovian theory or not. So I would like to introduce the following scenario. So consider a kind of like black box. It might be a very complicated system with many different inputs and outputs, but we focus only on two inputs. This is input, let's call it A. We can have a binary input, let's call 0, 1. Another input B, 0, 1. And then we have outputs. So inputs will be denoted by capital letters, and by small letters we will denote outputs. And right now, we ask the following question: whether it's possible to actually think about the system as two separate systems. So for example, we can think of a system that is made of 2 degrees of freedom, like a particle with spin, and this here system, let's call it property A, would describe spin of a particle, and we can ask two different questions about it. For example, spin along direction Z or spin along direction X. And
spin is not 2 degrees of freedom.
No. It's 1 degree of freedom. I mean, and another degree of freedom would be a position of this particle that has spin. And let's simplify it. We can, for example, ask 0 would be a question about position, 1 can be a question about momentum of a particle. And let's have simplified answers. So for example, the system is on the right or on the left, or it moves right, it moves left. And right now, we can have two possibilities. If we can indeed separate it, then what we will have here, we will have some, from this experiment, we will have some probability distributions, like given that we measured A, for example, A equal to 0 and B equal to 0, the outcome was A, for example, 0 and B, for example, 1. Then from this, we can also derive marginal probability distributions. And then, but what is important in this approach is that A and B can be really considered as two separable degrees of freedom, and they do not influence each other. Okay. Now consider another possibility. So this possibility is that actually we cannot divide it into two parts. So what we have here is actually a general, like a single degree of freedom M, and then we can have 4 possible actually questions about the system. One question is 0, 0, another 0, 1, 1, 0, 1, 1, and with also like 2-bit outcomes. So if, and this would be our assumption, so we will consider such systems and we will make assumption that it's indeed case 1. So if it's case 1, then we know that the output, for example, output A cannot be controlled by input B, and vice versa. Output B cannot be controlled by input A. And there is a very important result by Arthur Fine from 80s, who showed that if it's indeed like that, then it's possible to construct such a joint probability distribution for all questions. So despite the fact that in our experiment we can only measure such probability distributions, so they are marginal probability distribution, we still should be able to recover them from this joint probability distribution. So basically the problem of contextuality is, given this, can we recover this? So let me give you few simple examples of what I mean. I hope right now it will be much more clear. So first example is like something that I called explicit contextuality. It consists, it contains signaling. So imagine that here we will fix input A and then we will measure the output, and at the same time we will change input B. So for example, let's say that first we fix that input B was 0, and then we obtain the following probability distribution. And then we fixed input B equal to 1, and we obtain the following probability distribution. So if indeed A is independent of this choice, by summing up over B, we will get a marginal of A. But here we see that this marginal probability distribution in this case looks like this, whereas here this marginal probability distribution will look like this. So we see it's completely different. Therefore, by changing input here, we can observe some change here. All right. Now, let's consider another case. It's pure non-contextuality. So right now, consider the following thing. Again, we fix A, and then we measure, we fix first B equal to 0, and we get this probability distribution. And then we fix B equal to 1, and we get this probability distribution. And then you can see that right now, this joint probability, this marginal probability distribution of A, in this case and in this case, is the same, because we get A equal to 0 with probability 0.6, and A equal to 1 with probability 0.4. Moreover, what is possible right now, you can construct a joint probability distribution from which you can derive this and this. And it looks like that. So let me go right now to the third example, which is the most interesting one. And this is the one that I mean, something like that appears in quantum theory. Namely, right now consider all possible inputs to A and all possible inputs to B. And then we can have, for example, this probability distribution. In this case, we can have this probability distribution here, this, and here, this. And you can easily check that marginal probability distributions of A and B are always 1/2 and 1/2. So marginal probability distribution stays the same. There is no signaling. Still, for this system, you cannot derive joint probability distribution. You cannot find joint probability distribution. So, sometimes finding joint probability distribution is not an easy task. So can we find some tools that will help us to decide whether there is a joint probability distribution or whether there is no joint probability distribution? And such a tool is exactly a belt inequality, and this is a simple example of such a joint probability distribution. So consider again these outputs that we obtain during different measurements. And then assume the following thing, that, for example, if A prime equal B, if we have correlation here, perfect correlation, so if the output A prime is the same as output B prime, then this probability must be equal to 0. If B and A is also the same, then this probability must be equal to 0. But if A and B prime are also the same, are perfectly correlated, then this probability must be equal to 0. So you see that the right-hand side sums up to 0. But now, look at this picture here. If this is the same as this, if this is the same as this, and if this is the same as this, then these two must be the same. This is a natural consequence. So automatically you see that correlations are in a sense transitive. So these correlations imply this correlation. So it means that if these probabilities are 0, then in a Kolmogorovian probability theory in which all of these variables are jointly distributed, this probability must be also equal to 0. But right now, from this example, you see that you have here perfect correlation, here you have perfect correlation, here you have perfect correlation, here you have anti-correlation. So despite the fact that there is no signaling, a joint probability distribution cannot exist, because here you have this paradox. Although this is the same as this, this is the same as this, this is the same as this, these two are different. So this will imply a violation of this inequality. Okay, so basically in any experimental test of contextuality, what you basically have some system, let's say a particle. You just put this particle into some measurement device, and then you can use this measurement device to ask different questions, to measure different properties of this system. Let's call these properties A, B, C, and so on. And then we get a string of data. And then from this string of data, we can evaluate probabilities, and we can have some marginal probability. I mean, we will have some probabilities of single events, but of course, some properties can be measured at the same time, like this spin and position, for example. Some properties cannot be measured at the same time. Therefore, you will never obtain like a joint distribution. So you'll have various distributions, but then the goal is the following. Basically, from all these distributions that you got here, you try to construct this. If you can construct this, then you know that this system is describable within Kolmogorovian theory, and in this sense, the system is classical. If not, then you know that there is something wrong, so the system is non-classical, and this is what happens in quantum theory. So let me show you a simple example. So again, let's come back to this particle with spin and two spatial states. So right now, all the questions that we will be asking will be basically the questions about some states of the system. So it will be questions, is our system in this state or not? So basically all our measurements are basically associated with some projectors onto different states VIs. And then projectors, some projectors can be measured together, some may not be jointly measurable. If they are measured together, we say that they can be measured in the same context. And they can be measured together, of course, if the two projectors are orthogonal. Then what's also important is that each projector can be measured in more than one context. So for example, VI can be measured with VJ because these two are orthogonal, and VI can be measured with VK because these two are orthogonal, but VJ and VK may not be orthogonal. Okay, so therefore we have two different contexts, and this is the simple graphical example. So imagine that these are our four possible states because we have a four-level system. So VI is basically a projector onto this state. VJ might be projector onto this state. The second case may correspond to, again, VI is the same, but this time VK may be a superposition of these two states. So obviously, this cannot be measured with this, so these two examples make two different contexts, two different measurement contexts. Now, there is a very important thing, namely, since it's a four-level system, then in a single measurement we can have four different outcomes. So if it's a like maximally informative measurement, then we will have four different projectors, each projector of rank 1, and we know that definitely, I mean, assuming that our system will not disappear, we will not lose it. And in perfect situation, we will definitely get one of four outcomes. But definitely, two different outcomes cannot happen at the same time because of exclusivity. So it means that this implies that the sum of probabilities of events that correspond to different projectors, so of events in the same context, need to sum up to 1. So the sum of probabilities needs to be 1. So this is due to exclusivity. And now, important thing. If there is a joint probability distribution, and this joint probability distribution needs to be considered over all possible projectors, over all possible contexts, then this joint probability distribution needs to be defined over some set of events. And these events need to obey these exclusivity relations. So the question is, can we construct such a set that will obey these exclusivity relations? And this is an example. This was proposed by Adam Cabello and his collaborators. So for this for this four-level system, you consider the following 18 projectors. These projectors right now are labeled by two numbers. Each number corresponds to like a different context. So for example, V12 means that this projector can be measured in context 1. So with any other projector that has some 1, for example, this projector can be measured with this one. You see there is obvious orthogonality here. This can be measured with this one and with this one. So this 3 and this create a basis in a four-dimensional space. But for example, V12 can be also measured with any other projector that has 2. So it can be measured with this one, and this one. So you see that they also make a basis in a four-dimensional space. So basically, this looks complicated, but one can draw this helpful diagram. This graph shows you the orthogonality relations, the exclusivity relations between different projectors. Each projector is represented by a vertex, by this circle. And then, if 4 vertices are jointly measurable, so if 4 projectors are mutually orthogonal, they are in such a box, either orange box or a gray box. So for example, V12, V18, V17 are here in this box, V16, V67, V69, and so on are in this box. So you can see that in total you have 9 different contexts. 6 of them orange ones, and 3 of them gray ones. And right now, what's important, because of exclusivity and because of completeness, you know that definitely for a given context, you have like 4 events. And exactly 1 event needs to happen. So you need to, if you construct events, you need to assign truth values, and you need to assign truth value yes to exactly 1 vertex in each box. And so this will correspond to this black dot, and empty dot will correspond to truth value no. So if you try to assign these truth values to this set, you will easily find that it's not possible to make such an assignment that in every box there is exactly 1 vertex that has assigned value yes, and 3 vertices with value no. For example, you can see that in this box there are 4 empty ones. Okay, so this was example of contextuality, and this was basically the introduction. So let me go right now to our results. This is what happens, I mean, all of I said is what happens when you consider a single system. Here we are considering a single 4-level system. Right now, imagine that due to some reason, you need to consider more than a single system. You can consider 2, 3, or even some macroscopic number of systems, which is, this is actually quite relevant in the studies on macroscopic quantum effects. And right now, you perform some measurements on the system. So the first problem is to determine what kind of measurements you can do on such system. Another problem is that from this measurement, can you have enough data to test contextuality of this system? So let's consider a simple case. Imagine that all of these systems here, I just represented 2, but it doesn't matter. It can be 10 to the 23. So if you can distinguish between all of these systems, then in principle, you can address each system individually. This means that you can perform different measurements on each system. For example, on this you can perform some A1, B1, C1, and so on this A2, B2, C2. So basically, in this case, this situation, when you have distinguishable particles, in principle can be turned into n different experiments on a single particle. Now, interesting thing happens if we have distinguishable particles. Because right now, you cannot address them individually. You know that the set of possible measurements is limited. So we can have only symmetric observables. So right now, having this limited set of measurements and having this data, we ask...
I would
yes?
question this statement.
Okay.
There are, of course, experiments with, for instance, a number of ions in the trap, and addressing a single one is possible. Just because they are distinguished by position.
Yes, yes, okay, but
they are still indistinguishable. The state is symmetrized or anti-symmetrized.
yes, of course. But in this sense, they have labels, so they are effectively distinguishable.
No.
I mean, so I can say...
In the process of working with such a system, indistinguishability plays a major role.
Okay, yes, I understand. I mean, the wave function of everything needs to be symmetrized.
Sure.
Yes, of course. Of course. But what I'm saying is that basically, due to the fact that each system, each particle is in a different state, you can address them individually. Yes. So, okay.
Each particle is in all states, not in different states. That's the point.
All right, but what I'm saying is that effectively, you can treat such system as n particles. Each particle is in a different state.
No.
Sorry?
Well, maybe I can comment.
All right.
For example, in Bosons experiment, it's very essential, like the photons, you can have, they can have different degrees of freedom, and it's essential to make them indistinguishable in the sense, well, in the sense converse to what Paweł was saying, right? So, like having those degrees of freedom that label your particles, like, for instance, in this system makes it very easy, like, for classically simulate what happens.
Okay.
Sometimes people just care to make those, like, many systems very much indistinguishable.
Okay, I see the point. Okay, so maybe I was not clear enough. So here I assume that this would correspond to basically all system coming exactly in the same state. Like let's say that you have this situation may correspond to let's say n photons coming in the same mode, let's say apart from polarization. So you have say that you have n photons that occupy exactly the same state, and the only difference might be some.
The same state, but
Yes, exactly.
different polarization.
Yes, with different, and assuming that there are no other degrees of freedom, or even if they are, all of these degrees of freedom are exactly in the same state. So in this case, you cannot address them individually. That's my point here. Okay, I mean, this is.
They are in the same place.
Yes, exactly.
And addressing is typically requiring them to be in different places.
Yes, but for example, let's say that they might be in the same place.
What I'm saying is that there is a lot of situations where you can still address individually, and yet the system is symmetrized.
Yes, okay. With this, of course, I have no problem, and here I fully agree. All right. So, I mean, example might be like this. So exactly just like with, let's say that we have two photons in exactly the same spatial state, and in addition, let's say that they have the same energetic state also, so they are of the same color, but they have two different polarizations.
Same mode.
Yes, same mode, but different polarizations. So in this case, you cannot say which photon has what kind of which polarization. So if they were distinguishable, you could measure polarization of the first one, you could measure polarization of the second one. But in fact, what you can do, you can effectively measure basically like, so let's say that if horizontal polarization is associated with 0, vertical with 1 for the first photon, the same for the second photon. So effectively what you can do is basically measure this observable. So what's important, a system that in principle may have 4 different states, effectively right now has 3 states. So this is basically very well-known situation, but because of this contraction of the space of events, we will have some major issues. Okay, so what I'm going to consider right now is the same scenario that I considered before, but right now imagine that instead of a single particle that could be in these 4 different states, right now I have 2 particles that can be in two different states, and these 2 particles are indistinguishable. So let's say that they are bosons or fermions. First, at the moment, let's not worry about the type of the particle. So right now, we need to consider what happens with this exclusivity relation, because this exclusivity relation between events, between modes, was a crucial thing when we were proving this contextuality. So for a single particle, we knew that exactly one event in a context, so in a set of 4 events, needs to be assigned through the value 1, and 3 of them needs to be assigned through the value 0. In terms of particles, basically we can reverse it and speak of occupancy. So let's say if we have a single particle, then if we have 4 mutually orthogonal modes, 4 distinguishable modes, then we know that in such a context of 4 different modes, exactly 1 mode needs to be occupied by 1 particle, and 3 modes needs to be unoccupied. However, if we right now will have 2 particles, we know that 2 particles can, I mean, right now our modes will be definitely occupied by 2 particles. Particle cannot vanish. So right now, basically, this exclusivity becomes a conservation of the particle number. So what I'm saying is that whenever you are going to look at these 4 modes in some context, you will definitely find that there are 2 particles inside. Both particles might be in this vertex, maybe one may be here, another here, but definitely there must be 2 particles inside. So right now, let's check whether it's possible to assign 2 particles per context. We notice that it's not possible to assign 1 particle per context here. So this is this proof. So it means that we cannot construct a set of events obeying this exclusivity relation. Therefore, there is obviously no joint probability distribution, because this joint probability distribution must be constructed on such a set of events. But right now, what I'm going to show you that for 2 particles actually, and for 2 indistinguishable particles, it's possible to construct such a set of events. So these are 2 simple examples. Here you have 2 particles in this context, 2 particles in this context, 2 particles in this context. Basically, if you carefully check, you will see that there are exactly 2 particles per each context. So it seems that for 2 indistinguishable particles, there is no problem with contextuality. One important thing, if these 2 particles were distinguishable, so let's say one was represented by black dots and other was represented by blue dots, then of course you will again have a problem, because you will see that in some contexts you will have either 2 black ones or 2 blue ones. But as long as you don't distinguish them, as long as they are identical, you will observe no problem. And I mean, one interesting fact is that actually note that these assignments obey some nice symmetry that I depicted here. And now you already see that this assignment is valid for both bosons and fermions, because there is at most 1 particle per side. Then you may ask, what happens if you will have, for example, 3 particles? Will you have contextuality, or maybe this contextuality will vanish? So actually, in case of fermions, situation is very interesting, because for fermions we have this particle Hall duality. So if we will have 3 fermions per context, it's equivalent to a single Hall per context. So in each context we need to have exactly 1 Hall. So again, so if we consider a set of mutually orthogonal modes, 4 modes, there needs to be exactly 1 Hall. But since we know that 1 particle cannot be assigned, I mean, we cannot find assignment for a single particle, therefore we cannot find an assignment for a single Hall. So for 3 fermions, there's obviously no assignment, therefore there is contextuality in such a system. Now, in case of 4 particles, of course there is no contextuality, because basically you paint everything black. In case of 0 particles, you paint everything white, so this is also obvious. Right now, actually, in case of bosons, the situation is also interesting. I won't go into details, but so if you are interested, please go to this paper. But you can show that you will find contextuality whenever the number of particles is equal to is an odd number. Yes.
Just this Cabello scheme of measurements?
Yes.
Any particle
No.
number
Okay, so I should be precise, more precise. Here, this is about this Cabello scheme of measurements. And this is an open problem. I mean, this is actually quite a recent result, so there are not many follow-ups. So it'll be very interesting to find some system, for example, some set of measurements in which you could show, for example, that there is no contextuality for a single particle, but suddenly if you have 2 particles, you will have contextuality. Okay, so what you have here, right now you have the so-called state-independent contextuality. And what I mean by this is, again, there is no joint probability distribution, because simply you cannot construct the set of events on which this joint probability distribution is defined. So no matter what kind of quantum state you take, such a construction does not exist. But what I show to you is that actually for more particles, for 2 particles, such construction exists. But does it mean that I can explain measurements on every quantum state? So the answer is no, and I'm going to show you this is so-called Hardy type contextuality. So assume, so right now consider that I have two fermions, and assume that these two fermions are prepared in this state. So I definitely put one fermion in this mode and one fermion in this mode. And now, let's say that I will represent the state in this basis here. If I represent it, you see that there is non-zero probability that I measure one particle here and one particle here. This corresponds exactly to this term.
What does it mean? There is inequality?
No,
What is
okay.
the relation between psi and psi? Is it the same vector?
Yes, this is the same vector, but this vector is represented in this basis.
No, let's go back to the simple things. You have a
Okay.
basis in space.
Yes.
Now, is this basis made of orthogonal vectors?
Yes, this basis is
Therefore,
made.
the vectors are
Yes.
independent.
Yes.
How can you then transcribe one state into the other if the basis vectors are different in different directions? I don't understand.
No, I mean, this is basically change of basis. If I...
So you use different bases.
Yes. Yes, so okay, well, maybe I'll say...
This is the same state written in different bases.
Yes, exactly. This is the same state written in different bases. So basically, what I want to... The information that I want to convey right now is the following. This is how I prepared my state. So I chose this basis, and I put exactly one fermion here and one fermion here.
And you use a different basis.
And then I change my measurement apparatus, so I go to another basis. And in this basis, I can have 4 states, so 4 different modes. And then I check what are the occupation numbers of these modes right now for this originally prepared state. So in this new basis, this is this representation. And there is non-zero probability corresponding to this term that I will find one particle in this mode and one particle in this mode. So right now, assuming under this assumption of that the system is classical in the sense that there are no contextual...
But this has nothing to do with contextuality.
Yes,
It's simple mathematics.
yes, but right now I want to show you that from this some issue about contextuality is implied. Namely, assuming that these two states can be explained in this Kolmogorovian theory, so namely there exists a joint probability distribution that is constructed on these events that can be constructed right now, yes, then I will have the following chain of implication. So because this is my preparation, and because this is some possibility that may occur, so let's say that I perform a measurement and this is what I measured, then I know the following thing. If I instead measured in this basis, and again, assuming that there is this pre-assignment, that's a very important assumption, then because of the fact that there was already a particle assigned here and a particle assigned here, definitely in this basis, this position must be empty, this mode must be empty, and this mode must be empty. The same thing here, for example. I would find that this mode must be empty and this must be empty. So already what I see, that for example for this basis, is that I already assigned empty and empty to this mode, but since I have two fermions, these two modes need to be filled with particles. The same thing here. Already, what I have is that for this basis, I have assignment here and here, therefore these two must be empty. And now you see that when you consider this mode, already, when you consider this basis and this basis, already all modes have assignments. And in these bases, these assignments are empty, 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 and full. Therefore, one particle is missing. So
there is something extremely simple here, and then from this very simple stuff you derive some very complicated conclusions. You have fermions. Now, fermions are created in the state which you call 6, 7, 6, 9. I don't understand why two numbers. But anyway.
But this is because of this. Yes.
Yes. Okay.
Okay.
But anyhow, then you change the basis. That means that you express the creation operator as a linear combination of different creation operators.
Yes.
Correct?
Yes.
And then what has Kolmogorov to do with this problem?
Okay. Yes. So.
Because this seems to be simple quantum mechanics.
Yes. Yes. I mean, this is a simple quantum mechanics. But right now.
So what is the mystery?
Okay. So the whole mystery is the following. So I have here 18 different modes. Not all these.
Could you express this in terms of creation annihilation operators? I have creation annihilation.
Yes. So okay. In
different states.
yes. So in principle, I can right now, assuming that I have some kind of measurement devices and some kind of devices in my laboratory that can address one of these 18 possible modes. Some of these modes are orthogonal, some not. I have means to prepare my system in such a way that I put a particle in this mode or I will not put particle in this mode. Sure. All right? So this is how I prepared my system. Okay?
So
now,
you have two particles which you put in
yeah.
one mode.
Yes, exactly.
And second mode. That's
yes.
Then you change the creation operators.
Then I may change a basis. And right now my assumption is the following. So if the system is described by Kolmogorovian theory, okay, yeah, okay. So once more. Within ordinary quantum mechanics.
Which is based on standard probabilistic interpretation.
Okay, so what I can get in laboratory, I can get.
I have not seen a textbook in quantum mechanics where Kolmogorov would be mentioned.
Yes, because quantum. Yeah, I mean because quantum mechanics is non-Kolmogorovian theory in the sense that you don't have joint probability distributions.
True.
Yes, exactly. Yeah. So okay, what I'm saying is that in terms of quantum theory, everything is simple here because I can derive for you occupation numbers or probability distribution of occupation numbers for any of these 9 possible bases. And this is what quantum theory tells you. And right now I'm asking a question. Is it possible that there is a joint probability distribution describing all of these 9 bases? And from this joint probability distribution, I can derive this marginal probability distribution for each basis. So this is this assumption of Kolmogorovian theory that.
Is this a condition? Not every base, of course, has this property. Right? You are looking for such bases that have this special property.
The question is a bit different. So I have these bases here, and I ask if these bases have this property or not. So is it possible that all these numbers, all these occupation numbers for each basis can be derived from this huge joint distribution of all the numbers over all bases? So what I show to you that actually here this is not possible. Because if it were possible, and right now here's this chain of implication, if it were possible, if it were like that, it would mean the following thing, that because of my assumption of preparation, this is the occupation in this basis, then there is a possibility that I will measure this situation. So under this measurement, I will have this occupation number. And already from these 2 assumptions, I can show you that there is no joint distribution. Namely, because if this joint distribution existed, then for each basis, I should have 2 particles and 2 holes. But this implication shows you that this basis needs to contain 3 holes and 1 particle, 3 holes and 1 particle. So 1 particle is somewhere missing.
So apparently this is a condition on the states of the system. Not every state of the system
admits this description. Yes, exactly. That's the point.
These complicated pictures can be explained in a very simple way.
Yeah.
You have system of n fermions.
Yes.
And then you are looking for such states of these fermions that do have classical interpretation in terms of
yes,
joint probability.
exactly. And for such states that do not. Exactly. Yes. So now.
Can one really say in simple language what are these states? If you have 2 qubits, for example, which states admit?
I mean,
interpretation?
Okay, so here I don't think that the answer is that simple. I mean, because if you have two, I mean, okay, if you have two qubits, if right now we forget about the discussion about fermions and so on. If we have two qubits, then, for example, you know that some entangled states do not admit such description. But okay, okay, but the question is more complicated because I would say the following thing: for two qubits. And for what kind of measurements on these two qubits?
All possible measurements.
Okay, so if all possible measurements, then the answer is that it's not possible. And this is for example, this Mermin-Perez square proof, yes. But if you have a limited set of measurements, then yes. This is basically the implication of Glisson's theorem, if you consider all. Okay, so just quickly let me show you that the same type of reasoning can be done for bosons. So for example, assume right now that you create two bosons in this mode. So this is this situation. There are two bosons here, so this is n equal to 2, and there is vacuum, vacuum, vacuum. Now, if you represent it in this basis, you will see in this basis here, you will see that there is non-zero probability that you will find two particles in this mode. So assuming that this happens, then again, this chain of implications will show you that basically, definitely there'll be a single basis in which suddenly all particles vanished. So it means that this particular state cannot be does not admit this description, this classical description. Okay, so let me go right now to this main problem. So this problem of classicality of light fields. So basically, in these papers by Eberle and this earlier paper by Spriuv and there were some other papers, they considered some simple scenario. Again, a single four-level system, a four-level system. This was a scenario that was actually a local version of this famous Bell scenario. This is a CHSH scenario. This original CHSH scenario is the following. You have some source that emits two particles, so two qubits. One qubit goes to Alice, one goes to Bob. So you have obvious separation of these two degrees of freedom, A and B. And Alice can choose whether to measure 0 or 1, so A0 or A1. Bob can choose whether to measure B0 or B1, and there are two outcomes, which I'll here denote by plus and minus. Okay? So what they did, they considered a single system. So they simulated this four-level system that can consist, for example, of two polarization entangled photons, using a single photon that right now can travel in two different spatial modes and have two different polarization states. And right now, the measurement of A and B are not done in spatial separation, but are rather done in temporal separation. So they are measured sequentially. So we can decide whether first we measure A on B. So here we've decided that we first measure A, and then we choose whether to measure 0 or 1, and then we have an output. If the output is here to the left, we say that it's plus. If it's to the right, we say that it's minus. And then we measure B, but here we need to measure exactly the same thing. And then you see that here you can have output plus, output minus, plus minus. So for example, if I send this photon on this path and I measure it here, it means that the outcome of A is plus, outcome of B is minus, and so on. You can see that you have 4 different outcomes, 4 different paths.
So Alice makes non-demolition.
Yes, exactly. So basically, it's like, let's say that Alice first wants to measure polarization. So this is a system that consists of some polarizing beam splitter, like a calcite crystal placed in rotated properly, and then we have 2 different beams, and basically the beam determines the outcome.
So she really doesn't measure, because
well, she measures in a sense that she separates outcomes into 2 different parts. Yes, exactly. Yes, exactly. The measurement will happen here. And again, in the system, there is no Alice and Bob. There is only a single person. Oh, yeah. Yeah. So yes, the measurement happens here at this position. Okay, and right now, this situation is related actually. I mean, this scenario is related with 16 different measurement outcomes. And these outcomes can be labeled in the following way. So it means, for example, that we measured A0 and B0, and then we got outcome plus and outcome plus. This means that we measured the 0 and 1, and we get outcome A0 and B1, sorry, A1 and B0, and the outcome for A was plus, the outcome for B was minus, and so on. So you have 16 events because you have 4 different possibilities of choices here, and 4 different outcomes, so 4 times 4 is 16, but in fact, it's enough to consider only 8 out of the 16 events to show you that there is some contextuality in the system. So again, this is contextuality here, not non-locality. There is no spatial separation. So what we are going to test is this kind of inequality. Note that here we consider the following situation, that we measured A0 and B0 and that these 2 outcomes are correlated. So it means that we measure 0, 0 and the outcome was either plus, plus or minus, minus. Here we measured A0 and B1 and the outcomes are anti-correlated. So either minus, plus or plus, minus and so on. So that's why we need to only consider only 8 events. And right now, in order to derive this upper bound on these events, so this is this Bell inequality in which we are interested, is to consider exclusivity relations between these events. So for example, this is the same measurement, 0, 0 and 0, 0, but here we have outcome plus, plus and minus, minus. So this corresponds to either the photon will go on this path or the photon will go on this path. These are definitely exclusive situations. That's why exclusivity holds. But these 2 situations are also exclusive, because here we consider the measurement of A0, and here we consider measurement of A0. It doesn't matter that the B is different. And here, for example, you see that the outcome of A is different. Here the outcome is plus, and here the outcome is minus. So basically, this graph represents you all possible exclusivity relations. And right now, exclusivity relation tells you the following thing. If you assign a particle or truth value, right now let's consider a single particle, a single photon experiment. So we either assign particles to modes or truth value to events, whatever you want. If you assign truth value to one event, so let's paint it yellow, then any exclusive event, so it means event connected by an edge, needs to be assigned value 0. So it needs to be assigned vacuum. Okay? And then this graph is chosen in such a way that you can see that you can assign truth value 1 or a single particle at most to 3 events. You cannot assign it to 4 events. Okay? This is easy to see. For example, if you assign I mean, this is symmetric, so you can start here, then you immediately see that these 2 events must be assigned 0, these 2 events must be assigned 0, so you have arbitrary choice either here or here. So then, for example, if you assign here, then automatically this must be 0, and then you can assign, there are only 2 positions, but 2 connected positions where you can assign the 3rd one, and there is no place for the 4th one. Which means that these probabilities here must be defined over this set of events. Therefore, the sum of these probabilities is at most 3 in a classical theory. So this is under the assumption that this joint probability distribution exists. Now, interesting thing is that in quantum theory, the sum of these probabilities can give you 2 plus root 2, which is roughly 3.41. You can even consider some theories which are more contextual than quantum theory that obey this non-signaling relation, and so in principle you can construct such theory in which you get 4. But what's important, the bound is 3. And so basically whenever you violate this inequality, you know that there is no joint probability distribution, okay? And now, what happens in experiments? So in a quantum scenario, basically you have this photon, you place detectors, you consider different measurement settings, and you collect data. So you basically collect the number of clicks. And then you evaluate probabilities in the standard frequentist way. So you basically calculate the number of clicks, divide by the total number of clicks. And this is this probability of anti-correlation in this measurement, in this scenario when we measure A0 and B1. And then by repeating this for all possible settings, you will, and if you have a single photon and properly chosen measurements, you will get this result, 2 plus root 2. So you will violate it. And then the interpretation of this is that experiment is not describable within this non-contextual hidden variable. Okay, so this is a non-contextual hidden variable theory. Yes. Yes. Now, what happens in this Abeli experiments and in these other papers? They said, let's consider exactly the same setting. But right now, instead of a single photon, let's send a classical light beam. So we know that this is an optical setup. So the light beam should mimic the behavior of a single photon. The only difference is that right now, at the bottom, we will not hear clicks, but we will measure intensity of this light field. And then if we, in a sense, naively, but in a sense it's legitimate, evaluate probabilities using the following formula, that the probability is the probability of this event is intensity measured at this detector divided by the total intensity, total input intensity, then we will find that the sum over all these probabilities, so if we consider this experiment on all possible settings, will give exactly the same quantum value. So this is not surprising, but the question is what's the interpretation? Can this be interpreted as a violation of a Bell inequality? So I'm going to show you that no, because for this system you need to consider completely different Bell inequality. Because as I show you, Bell inequalities are derived on the special set of events. So again, Bell inequalities correspond to joint probability distribution over some special set of events. But right now, the system consists of many indistinguishable particles. So the set of events, due to this indistinguishability, changes. So let's go step by step. Again, if we have a single particle, we have this exclusivity structure, and from this exclusivity structure follows this inequality. So this inequality is valid, and the violation really shows that there is no joint probability distribution. Right now, consider the following situation. Let's assume that you have two photons, but let's say that these two photons are distinguishable. So let's say that one is yellow, another is blue. So in this case, you assign these events separately for yellow one and separately for blue one. In principle, you can do it. So it's like considering two different experiments. It's like basically putting first yellow photon and only later in another experiment putting blue photon. So it's like you have completely different inequality, like the first inequality for the yellow photon, second inequality for the blue photon, but since you get the same results, you basically average over them, but the conclusion is also valid, that here you can say that the system is contextual if you violate it, because this inequality is a valid inequality.
But you would get the same result if you would use the wave function for the Photon and propagation of this wave function,
yes,
which is not different from
yes,
classical light.
Yes, exactly. But right now,
so where is the difference that you emphasize?
Yes, so just one moment, I will show you. The difference is not in physics. The difference is in mathematics. In mathematics, well, I'm going to show you that right now you need to derive completely different inequality. So, I mean, maybe please let me go through the next two slides, and maybe then I'll try to answer this question. All right, so, and this is already almost the end. But right now, imagine that two indistinguishable photons come into this. So right now, we need to assign particles into exclusive events, and there is nothing wrong in assigning one particle to one event and another particle to another exclusive event, because simply there are two particles. So if they are indistinguishable, you can in principle assign particle to every event, and you will see nothing wrong in this. Therefore, this inequality actually will be invalid. And why? Because, so if we have a single particle, right now our set of events is basically like that. If we have two particles, you see that our set of, okay, so if we have two distinguishable particles, our set of events will be basically a product of events. But right now, because it's not a product, we have much smaller set of events, because, for example, here, we do not distinguish which is which, whether the first one is on the right, I mean, blue is here, or yellow here, or yellow here, blue here. Okay, and this, therefore, these assignments do not violate these exclusivity assumptions. And then, okay, so basically right now, what happens? You see that you have n photons. You have like a single photon per event. In total, you have 2 photons. So the average occupation number is like 1 per 2. So if you use this naive probability formula here, you will find that basically within this model, you can assign probability 1/2 to each such event. And there is nothing wrong in it. But if you assign probability 1/2 to each event, right now this classical bound becomes 4. So again, from the physical point of view, of course, the equation shows you that you will get this value 3.41. But in this situation, you need to consider completely different inequality, because from this upper bound is 4. Okay? So in this sense, with indistinguishable particles or with fields in which, right now, because here you consider 2 particles, but in principle you can consider n particles, and there is nothing wrong in assigning n½ particles to let's say this, to each vertex, because the sum of particles over exclusive vertices is n, is always n. Okay, so again, the conclusion is that in the end, the upper bound, the classical bound becomes 4, so you cannot violate it. You cannot violate it within quantum theory. You cannot even violate it within this higher generalized probabilistic theories, so these theories that are more non-classical than quantum theory. Actually, maybe some remarks here. Here I considered this special type of local version of CHSH inequality. But you can do the same reasoning, you can follow the same reasoning for any type of inequality. So you can consider this Kliatchko-Kanbini-Tsogli, Szynovsky, you can also consider this temporal Leggett-Gark inequalities. And the result will be the same. And another thing, this does not apply only to experiments with classical light. You will have the same things, for example, with in experiments with any type of light or any type of physical property that's basically like some oscillatory property or some vector property. Right, so my time.
It says you need 2 vector spaces that are under such a relation.
Yes, I mean, so you need to you need to have some system, and you need to impose some kind of a tensor structure. Yes, exactly.
Okay,
thank you.
Let's thank Paweł. And we still.
Physics, there is only one correct answer, because if you set up an experiment in which you send photons, then you can describe these photons by Maxwell equations. And that's it. There's one description which will be the same for classical and quantum.
Yes, but I mean, in Maxwell,
what else can you do?
I mean, but in Maxwell equations, you won't have like the collapse in the end.
What do you mean?
I mean,
of course I will have, because the wave will travel, and I know the intensity of the wave, which is the probability to find the photon.
Okay, but
whether you call it collapse or not doesn't
yeah, I mean,
matter.
okay, but so in the sense
So
you can.
Why there is this difference, which I don't understand? It seems to me that in a physical situation, there's absolutely no difference between the description in terms of photons and light, because they are the same thing. Photon is light.
Yes.
Light is made of photons.
I mean, okay, so again, the difference is in the set of...
Forget about the sets. I'm talking about the result of the experiment.
Yeah. Okay. So what I'm saying,
So what seems to be happening here, that you are considering situations that do not correspond to realistic physical experiments.
okay, so what I'm saying, it's not about the experiment. So again, experiment was done, and it was from the very beginning obvious what's the result of measurement is going to be. The issue was the interpretation of the experiment. So
do we have any other questions? One more question.
I have a remark, if possible. Okay. Well, at the end, it boils down to the fact that such a measurement done with the strong beam has nothing to do with checking whether quantum mechanics is right.
exactly,
On that, I think we agree. Now, I started off by saying that this is a little bit like with uncertainty relation, which also has its classical applications that had nothing to do with H-bar, and they have this very deep quantum mechanical thing. Now, I had these discussions over this point with Joe Eberle, and let me end with some anecdote. The discussion was heated, of course. He did not agree with me. And then at some point, lacking more or better arguments, he said, but you know, Aspen never raised this point.
Okay, and let's finish with this remark. Thank you very much for your talk.
Thank you.